A haystack full of needles, a scalable detection of IoT devices in the wild. I'm Jawad Saidi. Consumer IoT devices have become increasingly popular. It has been projected that the number of deployed IoT devices worldwide will surpass 17 billion by 2023. These devices provide a wide range of services and features to the users, from home appliances to voice assistant. However, with these features and services comes often significant privacy and security risks. For example, recently, some of these devices were used to launch one of the largest DDoS attacks that crippled part of the internet. Therefore, for a provider, in order to be able to mitigate these attacks, one of the first steps is to identify and locate these IoT devices in the network. But detecting IoT devices at the provider level is not an easy task. Traffic patterns across IoT devices are diverse, and some recent work have suggested to deploy some agents inside the premise of customers to detect deployed IoT devices. But these methods won't scale, especially when the number of customers of providers in order of millions. In the same fashion, active measurement approaches that scan the network for the deployed IoT devices won't work if the devices are behind the NAT. Deep packet inspection approaches can be more accurate, but they raise significant privacy concerns indeed. One of the easily accessible data sources for the providers is the flow capture utility such as NetFlow and IPFix. Providers are already collecting this flow data for their own operational purposes, like network monitoring. These data sources only contain packet headers, no payload, but they are often sparsely sampled. All these challenges constitute our research goals as following. Is it possible to reveal the presence of IoT devices with limited, passive, and sparsely flow data in the wild? And if yes, at what granularities can we detect these IoT devices? How fast can we detect them? And how are the IoT devices deployed today as seen in the flow data? The key insights of our paper is that devices that we studied have shown repeating patterns of communication that appeared even in sparsely sampled data. We generated detection rules using extremely limited packet fields that allowed us to detect devices from 77% of the studied IoT manufacturers in an ISP and IXP environment. Before going into details of our methodology, have a look at this figure. This figure shows the typical simplified communication pattern in IoT devices. The green boxes at the left part of the figure shows the subscribers of the ISP that have some IoT devices at them. In order for these IoT devices to provide their services, they have to be supported, and they have to contact some backend infrastructure in the internet. The intuition behind our work is that can we identify which type of IoT device is hosted at these subscribers by studying the backend infrastructure contacted by these IoT devices. Here is an overview of our methodology. We start by generating ground truth IoT traffic. Next, we check the visibility of ground truth traffic at an ISP vantage point. In the third part, we identify features such as domains, IPs, and port numbers that can be used to generate rules that can for detecting IoT devices. Next, we cross-check these detection rules, and finally apply our methodology on the data sets from a large European ISP and IXP. To generate ground truth IoT traffic, we set up 2 test beds in 2 locations that contain 56 unique IoT products from 40 vendors in 6 categories. We devised 2 types of experiments to stimulate devices to generate traffic: idle experiments and active experiments. Idle experiments, devices were simply connected to internet without being used, and in active experiments, we devised some automated interactions with the devices, for example, by asking a question from an Alexa device, what is the capital of Italy? The table shows the type of automated interactions with the devices. In order to make sure that the destinations and the traffic generated by the IoT devices are similar to the ones from the other IoT devices in the premise of ISP and is not biased to the location of the test beds, we VPN the traffic from the test beds to a household inside the premise of ISP and pushed back this traffic to the internet. We captured this traffic at the routers in the ISP and also at the home vantage point and test beds. Next, we wanted to check the visibility of the generated ground truth traffic at that ISP vantage point. We wanted to understand to what extent the IoT-related traffic from a single subscriber line is visible at ISP and reaches diverse set of servers, and whether the limited or the low sampling rate of net flow affects the device visibility. This plot, x-axis, shows the date that the experiments were executed, and the y-axis shows the unique number of visible IoT devices on a per-hour basis in the respective vantage point. The blue line shows the home vantage point, and the green line shows the ISP vantage point. If we look at the proportion of the visible IoT devices at the ISP, we identified that on average 64% of the active IoT devices were observed on a per-hour basis at the ISP level. We define activity as observing at least one packet to or from the device. Next, we identify features such as domains, IP addresses, and port numbers that can be used to generate rules for detecting IoT devices. Considering or using contacted IP addresses as observed in the ground truth dataset to generate these rules can be misleading for us. There are several reasons for that. Observe this figure. Here we have two types of infrastructure, dedicated and CDN or shared infrastructure. The dedicated infrastructure and the IP addresses associated with this infrastructure provide services only to the given IoT service. However, for the shared infrastructure or CDNs, they provide services to basically to anyone. And given the header-only nature of our data sets, it is very hard for us to detect devices that rely solely on CDNs. Here, device A contacts only dedicated, device B contacts a mixture of both, and device C solely relies on CDNs. This was only a part of the story. Even we can only see a part of IP addresses or portion of IP addresses in our contacted by the IoT devices in our ground truth dataset. And even these IP addresses can change at some point. Some of these IP addresses belong to the generic services that provide that serve content to a wide range of users, even humans. And considering these IP addresses can add too much noise to the set of subscribers that can possibly host an IoT device. We start tackling these challenges by looking at the domains first, and we classify and filter out domains that belong to CDN infrastructure or that belong to generic services. By employing passive data sources such as DNSDB, we can also capture the change in the contacted IP addresses, capture the change in between the IP to the domain or domain to IP mappings, and find the remaining IP addresses of a given domain that is contacted by an IoT device but not observed in the ground truth data. Here is a pipeline of our methodology that we use to filter out and generate the rules, filter out the domains and generate the rules. We started by filtering generic domains and classifying the remaining ones as dedicated or shared. And if we didn't have enough information in the passive DNS data sets, we used other data sources. For the details of this, you can check our paper. And then once the domains were classified and their IP addresses were classified as shared or dedicated infrastructure, we checked whether we have enough domains, and then from that we generated rules for detecting IoT devices. And finally, not all devices can be detected with our methodologies. Therefore, we offered 3 levels of detection: product level, manufacturer, and platform level. Product level is this most fine granular level of detection. When we say we detect a device at the product level, we know that this subscriber has a specific model like an Amazon Echo device. When we say we have a manufacturer level detection, we can only say a given subscriber has a device from a specified manufacturer, like it has a Samsung device, but we cannot say which type of product from Samsung it is. At the platform level, there are some part of devices that are using IoT specific platforms to manage their fleet of devices. And since this platform can have a lot of customers, i.e. IoT manufacturers, we cannot specifically say which product it is or which manufacturer it is, but we can say that it is a generic IoT device. In summary, we generated rules for 5 IoT platforms, 20 manufacturers, and 11 products that were in our test bed, which account for the 77% of the manufacturers that we studied. Next, we cross-checked the generated detection rules by applying them on the ground truth data from ISP dataset to measure how long it takes to detect our IoT devices from the test bed. And this heat map illustrates the result of applying these rules on the ground truth data at the ISP vantage point. The left axis, the y-axis in the left part of the figure shows the device name along with its detection level, and each box in this grid shows how long it took to detect the IoT device. The darker the color, the faster the detection. We measured the time to detection by varying the different conditions. Therefore, we have partitioned this figure vertically according to the device state. For example, if the device was in the active mode or it was idle, and we have partitioned this figure horizontally according to the number of domains that were tracked for the given device. The general takeaway from this figure is that active devices were much more detectable than the idle devices, and we detected some devices in order of minutes, even when they were in their idle state. In the last and final section of our presentation, we apply our generated detection rules on 2 data sets from a large European ISP and IXP. We report the results of how our devices deployed today as observed in the flow data. The first figure that I want to show you is the result of applying our methodology on 2 weeks of ISP data on a per hour basis, as shown in the x-axis. The y-axis of this figure shows the unique number of subscribers of this ISP in log 10 scale that had the given IoT device. The first takeaway from this figure is that we were able to detect more than 1 million subscribers that had Alexa-enabled devices. We also observed some diurnal patterns for Alexa and Samsung IoT devices. Alexa-enabled device is any device that responds to Amazon Alexa voice service commands. Next, we apply our methodology on the same ISP data, but this time with 24-hour time bins. What I mean by that is we consider 24 hours of traffic from a subscriber in order to identify which type of IoT devices are hosted at that subscriber. The first takeaway by doing so is increasing the observation period help detect more devices. While we have shown in this previous figure that it is possible to detect many Alexa-enabled devices within an hour, It was not the case for Samsung IoT devices. The main reason for that is that Samsung IoT devices are talking way less to the primary domains that were essential for their detection in comparison with Alexa-enabled devices. That is why that increasing the observation period helped detecting Alexa-enabled devices only by a factor of 2, while for the Samsung IoT devices, the number increased by a factor of 6. In summary, we have observed IoT activity for more than 20% of 15 million or more than 15 million subscriber lines that we had in the ISP. In previous figures, we reported aggregated statistics for 32 IoT devices. In this slide, we zoom in and break down those 32 IoT devices and report detailed statistics on unique number of subscriber lines for each IoT device. The dataset is again ISP dataset, and the time bin is 24 hours. The x-axis shows the date as it was in the previous figures, and the darker the color, the more number of devices detected or number of subscribers detected with that IoT device in that day. We have partitioned this figure horizontally based on the popularity of these devices according to the Amazon website of the country of ISP. What we see here is that the device popularity in the Amazon website and the ISP look correlated. For example, Philips devices are one of the most popular devices in the country, and we have detected more than 250,000 active Philips devices in our data set. For the devices that were not in the market, for example, we couldn't find them in any online website, naturally we don't see them in the ISP dataset as well. If a dataset does not have any ranking in the Amazon website, we categorize them as others. Our work has its own limitations. The first limitation is that we cannot detect IoT devices that heavily rely on shared infrastructure such as CDNs. The next limitation is that in order to generate signatures and detection rules for a given IoT device, we have to study it. And the signatures that we have generated up till now are only for a subset of IoT devices, not for all possible IoT devices. The next limitation is that if the domain names and IP addresses contacted by our IoT devices change, for example, due to an update to the device firmware, we have to also update our signatures and detection rules. The last limitation is that because we are using sample data, if the device activity is so small that cannot be seen in the net flow data or the flow captures, that device cannot be detected with our methodology. In conclusion, our methodology were able to detect IoT devices based on limited sampled flow data. We detected devices from more than 77% of studied IoT manufacturers in a large ISP and IXP. In fact, we detected more than 4 million subscribers that had both popular and not so popular devices. If you want to know more about our work, please visit the website of our work and you can download and apply our signatures on your dataset. With that, thank you for watching this video.